Yeah, hello everyone. So I'm going to talk about convolutional neural networks today, which probably every one of you knows. But I'm specifically going to talk about how they relate to symmetries, and they can actually be derived from symmetries of space and also be generalized in that way. And yeah, what you think about convolutional network is probably as something which processes images or something like that. So you have something like a field on some kind of space, for instance, a manifold. And if you have a non-trivial manifold, you have this ambiguity of which charts you can use to describe whatever you're doing there. So we need to be sure that whatever we are defining is independent from the choice of charts, which is why I'm talking about coordinate independent convolutional networks. And then these manifolds also may have symmetries. So for instance, for this Möbius strip, if you have some pattern on it, you could shift it along the strip and you want that this convolution operation commutes with these symmetries. And this is what is meant by equivariance. So let me start with an example. Let's say you have as an input point cloud representing a molecule, and then you would predict something like a force field at each point of that point cloud, and you train a model to do that. And you know that this physics here is independent from how you rotate the molecule. So if you have a transformed molecule, you know also your predicted point cloud or force field should be rotated accordingly. And in principle, if you have a naive neural network, it needs to learn this explicitly. So you need to show with each single transformed example input-output pair and train it, which takes a lot of time and lots of learning capacity. And if we talk about an equivariant architecture, we actually enforce that by design. So to do that, we need to make a group action on the input and output space explicit. And then equivariance just means that whatever network we train commutes with these group actions. So in terms of equations, you have that your map F acting on a transformed input should be equal to transforming the output of that map F. And this is what you can visualize in such a commutative diagram here. So if you take your input, you act with G and then send it through your network, it should be the same as first sending your non-transformed input through the network and then transforming your output. So you always have such a commutative diagrams if you're talking about equivariance. And this has two immediate implications. The first one is that the number of parameters of your model is reduced since you have some constraint, so they become easier to train. And the second implication is that such models generalize over all symmetry group actions. So let's say you learn this mapping on the top here, then you automatically know how the bottom mapping should look like. Since the bottom mapping by the commutativity of this diagram is simply an inverse transformation, then it's the top network and then you go back down with G. So these maps are tied to each other via equivariance. And the probably best known example of such an architecture are convolutional networks, since as you know, they commute with translations. So if you have such an image segmentation network and you take your input image and shift it, then your output segmentation mask shifts accordingly. Yeah.
But when you have pooling, they don't exactly commute with.
Yeah, true.
And so what's their property that there's symmetric enough, or what's your?
Yeah, so the convolution operation itself is equivariant, but as I said, pooling is not equivariant. Actually, pooling with
convolutional windows when you jump from one convolutional window.
Exactly. Yeah, so pooling can be split up into two operations. If you do pooling with a stride of 1, that is still equivariant, but then you do subsampling and that breaks equivariance.
Yeah.
Yeah. All right, so yeah, standard convolutional networks are translation equivariant. And I'm going to talk about 3 different generalizations. The first one is we want to be equivariant to more general symmetry groups. So, for instance, rotating an image, like you see what should happen if you reflect an image. Then we also look at more general manifolds. So if you have an image, for instance, defined on the surface of a sphere or any other manifold. And then finally, we look not only at global transformations on your space, but also independent local transformations at different points, which a physicist would call gauge symmetries. And as it turns out, all these 3 generalizations lead back to the same constraint on convolution kernels. So we end up with so-called steerable convolution kernels. And they will have certain symmetries in themselves, depending on whichever groups and representations you're choosing. So here you have rotation steerable kernels with certain rotational symmetries, or reflection steerable kernels for with reflection symmetries.
Yeah. When you say, so you're saying if you have forces, I don't understand what you're saying. In forces equivariance, it forces a particular symmetry on the kernel. Is that what you're saying? I assume that's what you're saying.
Yeah, so you enforce equivariance on the whole network, but it turns out that that implicity also gives you constraints on the convolution kernels. I will get there.
But not the kernel in the GP sense.
No, really convolution kernels here. Yeah. Yeah, I will do that. Yeah, but maybe I can ask who has an idea of what a convolutional network is. Okay, most people do actually know it, but I will show it.
Sorry, these pictures, should I perfectly understand them already, or will this?
No, I will explain these. Yeah. It's just like for now, just intuition of what is going to come. All right, so I will first start with equivariant neural networks in general, so not specific to convolutional networks, but the more general picture. And we will see that you will get certain so-called weight sharing patterns or symmetries in your neural connectivity if you demand equivariance. And then I will come to convolutional networks on Euclidean spaces, first with translation equivariance. So this is what you know as a convolutional network. And then we will generalize this to more general affine groups. So for instance, something like the Euclidean group or something like that. And as it turns out, this leads to G-steerable kernels, which I will explain then. And finally, we will look at how to generalize this to manifolds and to gauge symmetries. All right, so let's start with a multi-layer perceptron or feed-forward neural network. As you know, these are generic universal function approximators, which can map from any vector space to any other vector space. And yeah, they are built from matrix multiplications, Bayes summations, and then applying real nonlinearities or something like that. And you can throw in any features and then predict, for instance, class probabilities or logits of class probabilities. So for instance, we could take measurements like length, width, and thickness of leaves, and then predict whether it's species A or B. And of course, you can use that to classify images, since in some sense, images live in some vector space. So for instance, if you have an MNIST image, it has 28 square pixels, which you can just throw into an MLP and then predict which class it is. But the issue here is that these MLPs don't generalize over geometric transformations. So that works actually reasonably well, but what happens if you shift your image or if you slightly rotate your image is that the network gets entirely confused and it doesn't detect it anymore. And this is solved by making the network equivariant to these transformations. So some more examples. For instance, you could transcribe audio to text, and then you would probably want that if you shift your audio sequence in time, that also your text shifts around in time. Or let's say you have a visual stream input for control policy of a car, then you would probably want that if you reflect your visual input stream, that your control also reflects. So you would steer to the right instead of steering to the left. Or equivariance has been used for this game Go. Like if you want to have a policy for playing Go, then you know that if you would rotate or reflect your board, the rules of the game are invariant under these operations. And then your predictions should, of course, also transform accordingly. And as the last example, let's say you're at the airport and then someone controls your luggage and wants to see whether there are dangerous objects in there. So you flag which objects are dangerous, then this task should be equivariant with respect to permutations of these objects. Or for you as physicists, probably you would rather think about something like having a set of particles and then whatever you predict should be equivariant with respect to permutations of particles. So yeah, to explain how we build an equivariant network, I want to start with a simpler example, which is linear regression. So we have some ground truth curve and samples taken from it. And then we could fit that via polynomial linear regression. So linear means here linear in the parameters, not in the input. And this is what we would usually do. But let's assume now that you know your ground truth curve has a certain symmetry. So let's assume we know that f of minus x equals f of x. We have this symmetry and the reflections. How would you incorporate that into the architectures? Any idea?
Kill
Yeah.
the even ones.
Yeah. Actually, the other way around. Kill the odd ones, keep the even ones.
Also, you want it to be symmetric.
Yeah, symmetric.
But you said anti-symmetric.
Yeah, that's the second example.
Oops.
No, you're right. Yeah, if it's symmetric, then you want to keep the even ones.
Definitely something. Something has to go.
Exactly. Yeah. 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 So the point I want to make here is that equivariance gives you a constraint on your model parameters. So if you kill either the even ones or the odd ones, you enforce that symmetry into your model. You don't need to learn it anymore. You have less parameters, so you need less samples to learn it. Yeah, it's basically free lunch in that sense, if that symmetry really holds in the task. All right, so how do we apply that to neural networks? First, I define a feed-forward network basically as a sequence of layers. So we have an input feature space f in, and we want to map to an output feature space f out. And then we have a sequence of layers here and a succession of hidden feature spaces. So that is a feed-forward neural network. And then, of course, an equivariant network just has an input group action and a group action on the output space. And the network as a whole should commute with these group actions. But what we are typically doing in practice is we design each individual feature space in between as a group representation space. And then we demand that each individual layer is equivariant. And then if you stack these layers, the whole network becomes equivariant. So think about a convolutional network where you have like multiple convolution maps, and you have these internal feature maps here, and then each convolution is individually equivariant, and as a consequence, the whole network becomes equivariant. So to build something like that, of course, we need to specify all the feature spaces with group actions. So we don't only have vector spaces as feature spaces, but they're actually representation spaces. And then for a given layer, you have an input representation space and an output representation space, and you want to solve for those maps which are equivariant with respect to these representations. So as a first example, we can look at equivariant linear layers for matrix multiplications. So we have a map which sends an input vector x to w times x. And then we have some representations row in and row out, acting on the input and output. And what equivariance means is simply that W commutes with row in and row out in this sense here, right? So if you transform your input, that's equivalent to transforming your output. And you can take that constraint here and rewrite it in this sense, which shows you that actually W itself, the matrix itself, becomes an invariant under this strange tensor product representation. Right? So that means that W itself has certain symmetries, which people in deep learning call weight sharing patterns. So for instance, here you get a so that is a circulant matrix which corresponds to a convolution, where you have a one-dimensional grid with periodic boundary conditions, and then if that matrix should be equivariant with respect to shifting on that one-dimensional grid, you get this circulant structure here, which is kind of what a convolution is. And these two other examples here correspond to certain permutation representations. And the specific pattern which you're getting out depends both on the symmetry group you're considering and on the specific group representations which you're choosing. But in any case, you get certain symmetry patterns in your neural connectivity. You mean these ones here? Yeah, so in that case, I'm looking at a vector. Let's say it has like L elements, and you consider it as a sequence, and you have periodic boundary conditions, so it's kind of like a circle. And you want to be equivariant with respect to group representations, which shift these, shift around the circle. And that would be your row in and your row out. So for both, I want to have that representation which shifts on the circle. And then if you solve this constraint here, you get basically this matrix here. And the interpretation is kind of, this action on the input space would shift around here on your matrix, and the action on your output space would shift around rows. And the simultaneous shift, you want to be invariant under the simultaneous shift, which gives you these diagonal stripe patterns. And that, yes, this is the matrix W. Yeah, exactly. Yeah. And this is actually a convolution in the sense that if one row is a convolution kernel, then you take a convolution kernel and shift it around over your image or sequence in that case. And you see that each row is a different shifted copy of the same parameters. So in that sense, this is exactly a convolution. And the other ones here come from certain permutation symmetries. All right, so this is what we are going to look at later on, but for completeness, I just want to mention some alternative approaches how equivariance can be achieved. So probably the most obvious one is called data augmentation. And the idea here is that if you have supervised training samples, so you have an input sample and then a prediction, you apply a random rotation to it or some random transformation, and then you train on all these randomly augmented samples, and then in expectation at some point your model would become equivariant. But the issue here is that you still explicitly need to learn these symmetries, which requires some learning capacity, and it turns out that actually your model converges much more slowly. It has a worse final performance, and it's also less robust in the end. So that's easy to do, but it's not the best approach to use, specifically for very large symmetry groups.
But for just images, I don't know what's the state of the art in CNN for images, but does this beat that? I mean, I can imagine that images are not entirely translation invariant because they can. So what is the state of the art in image? Is it using that, or is it using just standard techniques?
So people use different things. A lot of architectures are still based on convolutions, which are by design equivariant, so they have these weight sharing patterns.
But apart from the schooling issue that we discussed in the journals, which is fair enough.
Even if not standard.
I guess the analogy to data augmentation would be that you just take a multi-layered perceptron, and then you take each image and shift it around randomly, and then train that NLP. That would clearly not work well, right? Since you have so many different translations, you would need to consider.
But I was just wondering in practice for CNN, I can imagine that for physical data sets, when you have a very rich symmetry group, does that technical say that anytime you try to do something intelligent to a neural network, then it actually performs poor, at least for real world data sets. So
empirically
we find that it actually works better.
Sorry,
it works better empirically. But it might make sense that at some point in the network, at a very late layer, you could break symmetries and then become kind of sensitive to whether you're at the top of an image where probably you have more sky, or at the bottom you have rather a street or something like that. So it's a good point. All right, then a second alternative approach is so-called group averaging or symmetrization. And the advantage here is that you can start with a non-equivariant model and you can symmetrize it by actually taking your input, applying all transformations in your group to it, or if it's a continuous group, then you would sample it, feed all these things through your network, then you realign them and somehow, let's say, integrate or max pool all these predictions. And this is guaranteed to be equivariant as well. But the issue is, of course, that this is extremely expensive.
Non-trivial equivariance or just invariant?
Yes, so let me write that down. So let's say you map from some vector space V to W with your map F, then equivariance just means you have some row V acting here and some row W acting there. And you want to commute, right? That's equivariance. And invariance is essentially the case where here you have the trivial representation. Right, so nothing is changing here. So you could write that as just having F here. This is the diagram you have for invariance. But indeed, yeah, invariance is a special case of equivariance.
What I'm saying is like when you aggregate that, can you actually allow for non-trivial equivariance beyond just the invariant? Because it seems to me it's just going to be invariant.
That would be equivariant actually, since if you rotate that by 90 degrees, also these all here are rotated. And then here you apply the inverse transformation from whatever you applied here, and then it also ends up transformed. And now a third approach is, actually not group averaging, but this is called canonicalization. And what people are doing there is they take the input and try to turn it into a canonical pose. So you need to have some heuristic or something which takes your input and predicts you what is canonical here. So for instance, if you have an image, it would try to rotate it upright or something like that. Then you apply your model, and then you can go back with your inverse canonicalization transform. That is of course cheaper, but it's not necessarily robust to find these canonicalization transformations. And actually there are topological issues since finding such, these are essentially orbit representatives, and we know in topology that there's no continuous choice of those possible usually. So you are guaranteed to get certain discontinuities in whatever you're trying to predict, which is not a good property to have. All right, so let's see how we can apply that to convolutional neural networks.
Pretty much. For the MFP example, you gave this linear story where the activation function was just set to the identity, and you had these intertwiners. It was all very clear.
Yeah.
Is there when you have the nonlinearity there, presumably there's no such simple mechanism, and you have to do something like you're going to tell us here.
Yeah, usually, so each layer needs to be equivariant.
Yeah.
Like for instance, nonlinearities, and there's you need to come up with certain nonlinear equivariant nonlinearities, and that depends a lot on which specific representation you're looking at. So, yeah, indeed, yeah. Usually the representations we're looking at are either unitary, and then you have certain nonlinearities which only act on the norm of these feature vectors. Right? Since if it's unitary, then the norm doesn't change, and then you do something like that. But that doesn't necessarily work very well, even though many people use it. The case where this all works out very well is if you have permutation representations. Since then you're just permuting around elements of your vector, and you can apply pointwise nonlinearities, just applying a ReLU or something like that.
Have something to do with shared lemma. If you have an irreducible representation, then essentially all invariants are just the multiplication constant multiple of the identity.
Yes, but so what I just said just applies to permutation representations.
I mean,
and Schur's lemma applies to to general irreps which need not be permutation representations, and also only to linear maps. Well, we are talking about nonlinear maps right now.
Yeah, but you build the nonlinearities with this linear maps with convolutional linear maps. At least. So
Schur's lemma is important to specify these linear maps, these matrices. But when we are talking about nonlinearities like ReLUs or something like that, you can't really use Schur's lemma there, except for if you build a nonlinearity which involves linear maps in it, then of course Schur's lemma plays a role in it.
For what you said about no continuous choice of orbit representatives, is that like, can you get almost everywhere continuous, or is it completely lost?
Almost everywhere, yes. Yeah. All right, so
but then we are always interested in almost everywhere. I mean, it's not necessarily that we will always have the full complete when we are doing a numerator.
Yeah, but you get issues if your prediction somehow in a certain regime starts changing discontinuously, then that's not a property you would want to have. All right, so convolutions were used in image processing already since many decades. And I have a very simple example here where you have some input image, and then the convolution kernel you can imagine as such a small filter mask, which in that case looks like a gradient in x direction. And if you convolve these two, you get such an edge-filtered image out. This is what you would do classically, but in convolutional neural networks, you parameterize these kernels here, and you have a bunch of them, and then you learn filter banks like these here, which you can imagine as little pattern detectors. And then if you get an image, you just slide all these filter banks over, the image and you get out certain feature maps of these responses. And then the next layer, you do the same thing again and again. And usually the story is such that you say, okay, I use convolutions in my neural network, and then you observe, oh, that's equivariant. But we are turning this around now. So we say we want to look at equivariant linear maps, and then from that you can derive that convolutions are actually necessary. So convolutions can be derived from symmetries. So to get there, recall that we have these two steps. First, we need to specify the feature spaces and group actions on them. And for convolutional networks, these are just spaces of feature maps. And then the second step is to find equivariant maps, which would be convolutions or bi-summations or certain nonlinearities. All right, so feature maps. To motivate them, we can first look at the discretized case. So just think about what you know from PyTorch or TensorFlow. If you have a feature map in d-dimensional space, where D would be 2, for instance, for an image, or 1 for audio, or D would be 3 for a voxel image, then you have such arrays or tensors of with D spatial axes, and then you have a certain number of channels. And as an example here, I have an RGB image where you have a certain height and width, x1 and x2 of the image, and then you have 3 color channels. So this is what you have in discrete space. But to treat that analytically, we will look at continuous feature maps. And they are just functions from RD, from your Euclidean space, to RC. So essentially, you assign such a feature vector f of x in RC to each point of space, right? All right, and then we need a translation group action, which is just defined such that the translated feature map evaluated at point x is just f of x minus t. So look at that figure here. If we take the feature map and shift it around by t along this blue arrow, then the transformed feature map at x came from x minus t. This is what this group action here is saying. And that is, by the way, called a regular representation of the translation group. And what I also want to mention is this definition actually includes point clouds. So I define everything in continuous space, but of course you can say your continuous function is actually summed from such Dirac deltas. So this also includes something like molecules or whatever you want to describe. All right, and now we can define convolutional network layers basically as any map which any translation equivariant map between feature maps. So if you translate your input, then you want that your output translates accordingly. And the general result we are getting is that if you demand translation equivariance, then you get a spatially invariant neural connectivity, which is what people call weight sharing, spatial weight sharing. And I give some examples. The first one is, if you start with a linear map and then you demand equivariance, then actually it turns out that you get a convolution. So as a graphical visualization here, in principle, you could have a different neural connectivity at different points in space. But once you demand equivariance, the neural connectivity needs to be shared. So this is essentially the same thing as getting a convolution kernel, which you slide over your image. And to make that more intuitive, I want to derive that property quickly. It's actually quite simple. It's very instructive to do that. Here.
The weight sharing is what we're showing initially with the color on the diagonals.
Exactly, yeah. Like the convolution kernels in what I showed before were like one row, and then each following row is basically a translated version. So it's like shifting around your kernel. And here it's visualized in a slightly different way.
Let's repeat it.
Yeah.
Very specific.
Yeah, exactly. Okay, so convolutions as translation equivariant maps. Naja? Okay. All right, so we start with a feature map. which are just functions f from Rd, as we said, to, for simplicity, let's just look at the scalar case for now. Later we can add more channels, but for simplicity, just 2R. And then I start with something which I call the 2-argument kernel. Okay. So a 2-argument kernel K, which is a map from Rd times Rd to real numbers. So it takes in 2 coordinates, and that is slightly different from what you usually think about as a kernel, but we will get there. Yeah, and then basically a convolution is things. First, it is a linear map. So we write K involved with F, evaluated at some point X in space. That is defined as an integral over Y. And we have K of X comma Y, F of Y. And you should think about that actually as a kind of continuous form of matrix multiplication, right? So if you have a matrix, you would have Mij, Fj, or something like that. But now we do it in continuous space, so you have an integral instead of indices you sum over. And that is not yet a convolution, that's just a linear map. So second, we have translation equivariance. Which just means that applying K to a translated input feature map at X needs to be the same as translating the output of the convolution. And as I will show now, this boils down to what you usually know as a convolution, where this here will become K of X minus Y, F of Y. It's just a different way of writing this.
The actions on RD.
Um,
Your translations in RD or in the output?
Yes, so the action on F, we have an action on feature maps, but it's defined as what I wrote down before. That let me go. Yeah, here. So translate feature map at X is defined as F of X minus T.
So it is in RD, and then you're writing it that way in terms of the symbol.
Yeah, exactly. Yeah. Okay, so now we can write that out. So we have the left-hand side, which, if we take this definition here and then have a translated feature map, that becomes an integral. And I call this variable dz now, since we will then substitute. And we get K of X comma Y. But now we need to plug in the translated F. So instead of just having F of Y, we get F of Y minus T. I'm sorry, this should be a Z. Right? This is just taking the definition and then translating my input. And now I substitute and call this variable Y. So this is the same as having integral dy K of X and Y plus T F of Y. And there's no Jacobian factor here. And then we can do the same with the right-hand side. where now here we act on the output of the convolution operation. So if we write that down, we have integral dy k of, and yeah, the output argument is x. So instead of having x comma y now, we get x minus t comma y and f of y. All right, and now we want that the left and right hand side are equal. And that should hold actually for any choice of feature map you're making, which implies that actually you can set these kernels here equal. So we get that k of x minus t comma y needs to be the same as k of x comma y plus t. We can rewrite that as k of x minus t comma y minus t should be the same as k of x comma y for each x, y, and t. So you see that this two-argument kernel here should be invariant under simultaneously shifting both arguments, which means that it actually only depends on the relative distance between x and y, not on the absolute positions. And yeah, so what we can do here is now, without loss of generality, we can pick t equals y. What happens then is that if you take k of x comma y, this is equal to k of x minus y comma y minus y. So the second argument becomes 0. So we can always shift to this representative where the second argument is 0. This thing only depends on the first argument, and then we can write that as some one argument kernel, kappa, which only depends on x minus y. So that implies we are plugging this into our original linear map that k convolve with f at x actually is an integral where we have this one argument kernel kappa of x minus y times f of y. And this is what you usually know as a convolution. So the point I wanted to make here is that yeah, you can start with a feature map and two-argument kernel, and you basically have this general linear map here. But once you're demanding equivariance with respect to translations, you can solve this constraint on k, and you end up with a convolution. So we derive the convolution from symmetries. And we start here in the scalar case, where this here is just a scalar feature map, but actually this can have C-in input channels. And this matrix here, if we want to map to C-out output channels, it becomes C-out times C-in dimensional. And then this convolution here, it's still such an integral, but these here are vector valued, these here are matrix valued. And then what comes out here in the convolution at some point x lives in C-out. And this is what we are usually doing in deep learning. Any questions regarding this derivation?
In your function where like output space, I mean,
Yeah.
the action does not act on the C it acts still in RD.
Yes, we don't have an action here on feature vectors for translations. So if you have a standard convolutional network, all that happens is that you shift around your feature maps, right? But there's no action on the feature vectors themselves.
Yeah.
But this is going to come if we look at more complex symmetries.
Acting on the locations.
Yeah, exactly.
And this defined equals in terms of this 1D thing, that's effectively just the math behind the stripes we're just seeing.
Exactly, yeah. For that case of matrices, you would have indices here, where then you would have k of index I minus j or something like that. Yeah. Right, so this is the story for linear maps, which gives you convolutions, but it works actually for any other mapping you're using in convolutional networks. So for instance, if you want to some biases, in principle, you could have a bias field where you have a different bias at each spatial location. But once you're demanding equivariance, you need to have a shared bias. You need to sum the same bias vector at each point in space. Or you could have different nonlinearities, like a ReLU at some point, and then you use a 10H at another point. But that would break the symmetry, so you need to use the same nonlinearity at each point. Or also for pooling, you could in principle use different pooling regions, but you need to use the same ones. So I guess the point is clear. You have this spatially invariant connectivity, which gives you translation equivariance. And as a physicist, you would actually call that the homogeneity of the laws of physics.
Just a literature question, because I'm not in the know. I heard, I've heard many times, I heard Taco even in 2019 giving a talk similar in spirit, but there's theorems in 2023. What was it that sort of happened that was more general in this more recent work?
Yeah, there's a whole line of works. Initially, we started with group convolutions, which only work on groups. Then we moved to homogeneous spaces, and at some point to manifolds. And also we went to, that will come in the end. And yeah, in these initial works, he was also only talking about regular representations, which correspond to group convolutions. But here we are looking at arbitrary representations.
So it's moving towards more and more general, fewer and fewer assumptions.
Yeah, yeah, exactly.
Thanks.
All right, so this was the story for translations, but now we can start and generalize this to other symmetries like rotations. So yeah, until now we just looked at translations of space, but let's say you would want to include something like the orthogonal group, so you have rotations and reflections. Then you get out in total this Euclidean group here, which is defined as a semi-direct product of translations and the orthogonal group. And we are actually looking at more general class of symmetry groups, which are called affine groups. And here we have the semi-direct product where the orthogonal group is replaced by any matrix group, which is a subgroup of the general linear group. So this could model in particular rotations and reflections, but also shearing or yeah, what is the other example? Scaling or something like that. And now again, we need to come up with certain group transformations which act on our feature spaces. And yeah, we are talking about something called feature vector fields. And as functions, they are just like feature maps. So we have these functions here which assign a c-dimensional feature vector to each point of space, just like before. But the difference is that now we have an affine group action acting on them. And these actions are actually defined by something called field type, which is a G representation rho. So to explain that, we can look at scalar and vector fields as the most simple examples. Yes. Yeah, so yeah, D is the spatial dimension, and then C is the dimension of your feature channels.
Just to clarify, maybe it's clear already what you said. When you said feature vector fields, the vector is in the RD space with respect to the group, not R sub.
I call them feature vector fields since actually you have fields of feature vectors. So you have c-dimensional feature vectors, yeah, but not only one feature vector, but a whole field. That is what I mean. So these are actually associated vector bundle sections.
Yeah, but that's in RD, right?
RD is the base space, yeah, in the manifold. Yeah.
On the manifold.
Yeah, you have a field on a manifold, yeah, a field of c-dimensional vectors on a manifold. Yeah. For instance, yeah. Yeah. Yeah, exactly. And then in hidden layers of your neural network, you have like 128 or 256 channels. Yeah. Yeah, so let's look at scalar fields. And here we have, yeah, a field on RD, but each scalar is just a one-dimensional feature. Yeah, a scalar field transforms such that you see it here. Basically, each scalar value moves to a new position. So we can write that as the transformed field, where T is a translation and G is this G element. Just think about rotation. For instance, then the transformed field at X, the scalar came from TG inverse X. So in the picture, your transformed field at some point X, this value came from TG inverse X, right? very simple for a scalar field. But if you have a vector field, there's one additional thing happening. So TG acting on the vector field now is taking the vector from TG inverse, just like before. But then in addition, we also act on our channels, right? And this is since you don't just take the vector and move it up here, but also the vector itself rotates, right? So you have this additional rotation on the channels of your vector. And this is why you need to have that G acting on the channels of your feature maps as well. And yeah, if we analyze this, in both cases, we have this spatial action here on the base space, and then we have some action here on the channels, which in this case is just G multiplied to it. Here we multiply 1 to it, which corresponds to the trivial representation. And that actually already tells you how this generalizes to other cases. We can define a feature field of what I call type rho, just such that if rho is a C-dimensional representation, you have C channels, and then yeah, this just transforms according to rho of G. So for instance, if you want to model something like a tensor field, then rho is just a tensor representation. So here I have some examples. For instance, if you have fluid flow, that's a vector field, which means rho of G is just G. Or if you're interested in an electromagnetic field strength, that is a bivector field, or an antisymmetric 0,2 tensor field, which corresponds to some subspace of such a tensor product representation here. The same holds for diffusion tensor images. They have no symmetric positive definite 1,1 tensors, which are just some representation. Or probably you know tensor field networks, which are a quite popular architecture for rotation equivariants. And they basically use Wigner-D matrices or EREBs of SO3 as features. And now we can again define our convolutional network layers, which we call steerable CNN layers in that case, as any affine group equivariant maps between such feature fields. And again, we have this result. So before we had that translation equivariance gives you an translation invariant neural connectivity. Here we have the same, which is that affine group equivariance gives you an affine invariant neural connectivity. And to understand what that means, recall that the affine group was defined as the semi-direct product here. So in particular, it has the translation group as a subgroup, which means that whatever we found before will again apply. So in particular, we again get spatial weight sharing or convolutions. But then you have these G symmetries on top of it, which give you constraints on the convolution kernels themselves. And yeah, they lead to these G-steerable kernels here.
Question asking to say bundle.
Well, in bundle language, this symmetry, FG symmetry here, will become a principal bundle automorphism. And G is the structure group of the bundle. Yeah, and what you see here in this table is like lots of architectures from the literature on equivariant convolutional networks. Basically, everyone comes up with their own method to design something for specific symmetry groups and specific dimensionalities of spaces and so on. But as it turns out, these are just different choices of spaces and group representations. And it's all described by what we are doing here in this generalized setting. All right, so now the main part of my talk will be about G-steerable kernels.
Can I ask actually about that? So I think part of what you're saying is if you just require only like linear equivariant maps, then they must take the form you have, just as every representation, like anytime you're equivariant, there's some representations on both sides. And you're just saying whatever you develop, I think, in that world applies to whatever people were doing. Is that like the
almost. The thing is that we also, like we consider a whole family of representations, but actually we are considering induced representations, right? And induced representations correspond to feature fields. Like for an induced representation, you have a field of feature vectors where at each point they transform according to some rho of G. But you could also encode, let's say, an image just by a representation which somehow does not resolve the spatial symmetries as a field, and that would not be covered here. But usually people always work with feature maps or feature fields, and this is why we covered that.
I see what you're saying. But either way, you're saying this is like a theory to underpin the linear kind of case. And of course, in principle, you could ask what the nonlinear representations are, but like, you could maybe produce examples, but it's unclear how to treat that systematically.
Yeah, you were saying nonlinear representations. I don't exactly know what would come out there, but this actually comes from having linear maps between representation spaces. Yeah. Yeah, but yeah, indeed, people look at something like transformers, which are nonlinear, and then you have other methods to make them equivariant, but there's no systematic framework to describe that until now.
Okay, I understand.
Yes, and I'm mainly talking about the linear case here.
Yeah, I understand.
Yeah. All right, so first I want to give you an intuition for what a G-steerable kernel is. So let's start with a non-steerable kernel. If you have a standard convolution kernel, then essentially what it is doing is it takes a patch of your input feature vector field and summarizes it into some feature vector f at x, right? And if you have a steerable kernel, then it has this additional G-symmetry property, which is such that if you G-transform this input patch, then the output feature vector, which your kernel summarizes, transforms according to rho of G. So that is the intuition you should have for G-steerable kernel. Yeah, so G-steerable kernel by itself encodes these G-symmetries. But now imagine we take that kernel and convolve with it. Then you add translation symmetries to it. So you get G-symmetries and translation symmetries, which together give you an affine group equivariance.
Missing why we introduced the word steerable. So it is equivariant. Is this just one particular construction of an equivariant network?
Yeah, Taco started calling it steerable at some point, since there's literature from 1988 or so. There was a paper by Adelson Freeman, which is called the design and use of steerable filters. We just call that term and we stick with it.
So it's a particular construction of an equivariant.
Yes, but yeah, we just use that term steerable kernel, but you should call it equivariant kernel probably.
So it's equivariant, but when you're referring to it, it's the construction that you guys have been working with rather than some of the other ones in the literature, and this is general and linear. So.
Yeah. Steerable kernel is just, or steerable convolutional network is just the name we picked at some point. And
so I shouldn't worry much about that.
No, don't think so. Just think equivariant kernel, that's fine. Where the equivariance is not with respect to this global symmetry group, the affine group, but with respect to the this local stabilizer subgroup or structure group G. Right? So only rotations, but not translations.
G acts on the terms.
Say it again.
G acts on the terms.
Yes, exactly. Yeah. Well, it also acts on the base space. Yeah. All right, so now we can look at the mathematical definition and again start with the discretized formulation of convolution kernels. And as again, we have such a multidimensional array where we have d spatial axes as before, but then each kernel is actually a matrix value for a convolutional network. So if we want to describe that in the continuous case, we get such maps here, which now don't go from RD to RC, but actually you can get something like a matrix valued field, and we visualize that as a matrix of kernels in some sense. And yeah, that holds in general, but now if we demand G-steerability on top, we get this funny looking constraint here, which is saying something like if you G-transform your kernel spatially, so let's say you take your kernel and you rotate it, then this spatial transformation corresponds somehow to a non-spatially transformed kernel, but acting on rows and columns of the kernel with your input and output representation. So if you look at this thing here, this kernel, you can imagine that if you spatially rotate these harmonics, that can somehow be represented by mixing rows and columns of that kernel. And then you have this determinant factor, which is just a volume scaling factor of your symmetry. And yeah, so essentially the space of such convolution kernels is a vector space. You can take kernels and sum them and linearly combine them or scale them, so they form a vector space. And then we have this G-steerability constraint, which is a linear constraint. So what it does is it constrains your full kernel space to a linear subspace, which implies that we can actually solve for a basis of steerable kernels and then expand our learned kernel in that basin. So here you have an example of strict harmonics, which you get out for SO3 rotation equivariants. And yeah, then any learned kernel can be a linear combination of these basic spherical harmonic kernels.
Can I ask, like, in what sense can solve? Like, it depends on the group, presumably. Like, there's some general algorithm, but maybe no formulas, right? Is that?
So I will come to a Wigner-Eckert type theorem later on, which gives a complete classification of these kernels for any compact group. And before coming to that, I will give some more specific examples. But that is kind of the main juice of the whole steerable CNN theory, how to solve that kernel constraint.
I see.
Yeah. So yeah, the first example I want to look at are reflection steerable kernels. And that is a very simple case since the reflection group only has two elements. One of which is the trivial group element and the other one is the reflection. So that is very simple to solve. And yeah, in particular, yeah, you have the reflection group with E, which is the trivial group element, and R, which is the reflection. And then you have this property that R squared, if you reflect twice, it's the identity again, which can also write as R inverse equals R. So that simplifies our kernel constraint, which in general looks like this. But now this determinant factor drops out, since for reflections it's just one. Then we have here that, well, it needs to hold for any group element in your group, but you have only two elements. One is trivial, so that one doesn't count. And then it only needs to hold for this single reflection group element. And then you also know that row of reflection inverse, due to that property here, is just a row of reflection, which means you get this very simple constraint here. And now we can look at different representations of field types and try to solve that kernel constraint. So let me first write down the constraint again. We have that a spatially reflected kernel is equal to acting with row out of the reflection on the non-spatially transformed kernel, and then you have row in of R. And we are looking at three different field types. The first one is a trivial representation, which corresponds to scalar fields. And then what happens if you act on your field is just that it's spatially reflected, but the feature values don't change. If you have this sign flip representation, which assigns -1 to the reflection, then you get such fields which, if you reflect them, the feature vectors move to a new position, but they also negate. And then as a third very simple representation of the reflection group, you can look here at the regular representation, which just acts now on two-dimensional feature vectors in such a way that if you act with a reflection, these two channels swap. So I draw that here with these this blue and green channel. And if you reflect that field, then you get a green and blue channel. So they also permute. And now we can take any input and output representation from there. And any combination will give you some constraint on your convolution kernels. And we will look at some now. So the first case is the most simple one. If you want to map from a scalar field to a scalar field, you get such symmetric kernels. And we can derive that here. So scalar to scalar. There you have that k of Rx equals row in and row out of reflection are just one for the trivial representation. So you get 1 times k of x times 1. So you just get k of x, which means that the reflected kernel is equal to the non-reflected kernel. So you get such symmetric kernels here. That is what the steerability constraint tells you in that specific case. And that is probably intuitive, since if you take that non-reflected image here and convolve it with a symmetric kernel, you get a certain output field. And if you then take the reflected input, this kernel here is entirely insensitive to that you reflected your input. So you get exactly the same output, but also reflected. So it satisfies that property, but here we derived it from the kernel constraint. Then as a second example, we can go from scalar fields two pseudoscalar fields. And now we get that k of Rx equals, now we have here a row out being for pseudoscalar fields -1 times k of x times +1, since we have a scalar field as input. So we get minus k of x, which means our kernel is antisymmetric under reflections, right? And this is what I'm trying to visualize here. And again, the intuition is for your standard image, you get a certain output. And then if you reflect your image, this kernel is exactly negated to what you had before. So you get an output which transforms like a pseudoscalar field.
What does this mean in practice, that you are learning both images and negatives?
You just need to design an equivariant network. You have the sequence of layers, and each intermediate feature space somehow needs to transform according to some group representation. And this is really a hyperparameter that you have to pick. So usually if you build a convolutional network, you need to say, oh, I want to have 64 channels in that hidden feature space. What you do here is you would say something like, I want to have 32 scalar channels and then 32 pseudoscalar channels. And this constraint tells you basically how you map from scalar to scalar or from scalar to pseudoscalar, like basically between these representations you are choosing. It doesn't tell you which representations to choose, but you have to choose some group representations according to which your hidden features transform. Yeah, that's an empirical question.
We haven't done it.
Exactly, yeah. It depends on the nonlinearity. So if you have any permutation representation, you can, as I said, use any pointwise nonlinearity. But if you have something like a pseudoscalar field, then if you apply ReLU, that does not actually commute with these sign flips. So they need to come up with a different nonlinearity you're applying. And yeah, as long as you don't find great nonlinearity for that specific choice, probably you shouldn't use that representation. But we don't have any systematic answer of what you should use. We just know that permutation representation, specifically the regular representation, works very well in practice. But the issue is that for high-dimensional groups, the regular representation becomes extremely large. Okay, and then as a third example, let's look at a map from a scalar field to a regular feature field. And the difference here is now scalar to regular. The difference is that now K is a map from, in that case, R2 to R channel out times channel in, which for the regular representation, we have two output channels, one input channel for a scalar field. So we have that 2 times 1 kernel here. And the constraint looks such that the reflected kernel now has two components. So you have like the first and the second channel. And if you reflect them spatially, this should be the same as acting with this regular representation. The output 0, 1, 1, 0, K1, K2 of x times 1, you can drop. But that is essentially K2 of x and K1 of x. And yeah, you get that the reflected first kernel channel has to be equal to the second kernel channel, and the reflected second kernel channel has to be the first kernel channel. So that's actually the same constraint. And this is what is visualized over here. So you have two channels, since you want to map from one input channel to two output channels, and they are a reflected copy of each other. So this is the specific form of weight sharing you're getting here. And yeah, to get an intuition again, if you the blue output comes from this input scalar field with the first kernel channel, and then if you reflect your input, the relative orientation of this reflected input and the reflected kernel channel is the same as here, the non-reflected input and the first kernel channel. So the blue output goes now in the second slot, and the green output goes into the first slot. So again, this kind of constraint satisfies exactly what we wanted. And now you can play that game with any other combination of input and output representations, and then you can build these tables here which tell you how your kernels need to look like. So for instance, if you would go from a sign flip pseudoscalar field to a regular field, then you have this spatial reflection, but also some negation of your kernel channel. All right, and now we can do that for other symmetries, and I will just show you the results without derivations. So for instance, if you have images and want to be SO2 rotation equivariant, then the first observation you can make is that you have a rotational symmetry constraint, which only affects the kernel's angular part, but not their radial part. And then a natural basis to expand your kernels is this basis here of circular harmonics. And you will get, like this stability constraint will give you a constraint on these harmonics here, on the spectrum you can choose. And as a very simple example, we can again look at maps from scalar field to vector field. And it turns out that you're only allowed to take circular harmonics of frequency 1 for that mapping. And that actually corresponds exactly to a gradient operator. And then you can go back from vector fields to scalar fields. Again, you get a frequency 1 kernel, which corresponds to a divergence operator. If you want to go to from scalar to scalar, you get these frequency 0 kernels, which corresponds to a Laplace operator. And then finally, if you want to go from vector to vector fields, you get actually now 2 solutions with frequency 0 and frequency 2. And they correspond to this Laplace on the diagonal or this gradient after divergence operator. Yeah, and if you choose more complex representations here, like tensor representations, so you get more complex solutions with higher frequencies. But this is like for these examples, that's the most general solution you can take.
So I think I'm going to ask the same question I asked before, but I'm actually not sure if it's the same question. So what's the most general G for which you can write down the answer?
The constraint exists for the general linear group, and we derived solutions for any compact group. So any subgroup of unitary or orthogonal groups.
I see.
Yeah. And we have a different way to implement that for something like the Lorentz group or so, and I will come to that later. Yeah.
From the perspective of effectiveness, the way you do this, like the operators that you get, they seem quite like, I mean, intuitively, I feel like they will be very hard to do. Right.
Well, they're easy to learn, but maybe they over-constrain the model.
Yeah,
that's probably what you have to say. Right?
Yeah, so instead of working in the image representation, if you go to the point cloud representation, there are more this like classical groups ways of doing equivariance in there. Yeah. Compared to that, like, do you have a notion like which one is more? Because I feel like
they're actually doing exactly this, but in 3D.
Yeah.
So this is now if we go from
I understand the group is the same, but what I'm asking is like the effectiveness of learning some function, which is equivariant to invariant. Which one do you feel is
invariant in which way?
So this group invariance, SO3 group invariance.
So we built SO3 group equivariance.
Yeah.
And this is state of the art actually. So everyone working on point clouds and molecules is actually using exactly this approach. So yeah, we can do the same now in 3 dimensions, where you have this SO3 constraint, and then again, if you go from scalar to vector fields, you get these spherical harmonics now with 3 elements, which again correspond to a gradient operator. Again, frequency 1 if you go from vectors to scalars. Again, frequency 0 for the Laplace operator. And then if you go from vector fields to vector fields, now it looks slightly different. Now you have frequency 0, 1, and 2. And probably you already see that this kind of corresponds to, you're going from a vector field to a vector field. Vector fields correspond to SO3 irreps of order 1. And then here you get orders 0, 1, and 2, which corresponds actually to the irrep decomposition of the tensor product of your input and output representation. And that is exactly what is happening here. And just as a side note, I have all these differential operators here. And actually, there's some precise mapping from our steerable kernels to equivariant differential operators in this paper there. And yeah, it's kind of funny that you know all these operators from physics, but these operators appear in physics exactly due to the symmetries of physics. You probably never thought about it that way, but yeah, you wouldn't have something like dx squared plus dy to the power of 9 or something like that, since this does not respect the symmetries. But just like the Laplace curl and gradients after divergence operators respect the symmetries. All right, last example are Lorentz group steerable kernels. So the difference here is, as you know, that in Euclidean space, you have this Euclidean metric where your orbits of constant distance from the origin are circles or spheres. And in Minkowski space, you have these hyperboloids. And then you get very similar solutions. So for instance, if you go from scalar to scalar, here we get rotation invariance, or like these frequency one solutions. And we get something very similar in Minkowski space. But now you have kind of such harmonics on hyperbolic sheets in your Minkowski space-time. And here you have visualizations for the higher dimensional generalizations. So yeah, R3 or Minkowski 1,2 space-time. Right, so you were asking about the general solution, and that we found by looking at some analogies between quantum mechanics and deep learning. And the first observation you can make is that actually, yeah, in quantum mechanics you have quantum operators which act on states. When in deep learning you have these kernels acting on features. And both need to satisfy these constraints. In our case, we have this steerability constraint on kernels. And in quantum mechanics, the analog is this so-called representation operator constraint. So specifically here, I'm writing down a vector operator constraint. So just imagine that Aj would be, let's say, linear momentum operators. Then you have momentum P1, P2, P3, and they mix in a certain way according to this representation here. And yeah, here you have this, yeah, you have basically a mixing of operators, which is equal to acting on the input and output space of the operator. And that corresponds exactly to our steerability constraint. And another analogy is that these symmetries actually imply selection rules between quantum state transitions in physics, while we have these selection rules where yeah, certain kernels only allow to map between different, like specific representations of feature fields. So there's something very similar here. And this is, yeah, these selection rules are described by matrix elements of these operators or kernels, and specifically the non-zero matrix elements. And the theory describing that is the Wigner-Eckert theorem in physics. We have a generalized version of that for steerable kernels. So yeah, we are looking at matrix elements. Here, basically, you take an operator and then you look at matrix elements mu nu, which for the kernel is just like the mu nu entry of your matrix valued kernel. And if you have a certain symmetry constraint on your operator or kernel, then this reduces the degrees of freedom of these matrix elements. They are somehow coupled to each other, which is described by the Wigner-Eckert theorem, which for SO3 and so-called spherical tensor operators, which means that this A here, if you have order J, you have two J plus one operators, which mix according to Arabs of SO3. Then, yeah, in principle, the number of matrix elements you can get here is 2 capital J plus 1 bras here in your basis, 2 L plus 1 cats, and you have 2 J plus 1 operators, so you get a whole bunch of matrix elements in principle. But due to symmetries, it turns out that actually there's only one single matrix element, and the rest is here these Lebsch-Gordon coefficients, which come from the tensor product. So essentially what happens here is that this representation and this representation couples via a tensor product, and then you project into a Arab basis. And most of these coefficients are actually 0, and the other ones are somehow coupled. And for G-stable kernels, we get a very analogous result, where the matrix elements are again determined by Lebsch-Gordon coefficients, just like here. And then where the generalization of these matrix elements are actually anamorphisms of irreducible representations that's one-to-one the same, only that we don't only look at SO3 where they are just complex numbers. Here they can be higher dimensional, but these are the learnable parameters. And then what comes in addition is that your kernel is not by itself irreducible representation like this here, but it's some function on a circle or on like the spherical shell or something like that. And you first need to decompose that into its irreducible components. And this is done via something called Peter-Weyl decomposition. And then, yeah, if you have a certain group which you chose, and you know this Peter-Weyl decomposition, you're basically your harmonics of the group, you know your Clebsch-Gordon coefficients and the anamorphisms of irreducible representations, you know exactly how your kernel matrix elements look. So you can implement that, and we have a library for that.
You just take polynomials? So what degree?
Say it again?
What degree on?
That's again a hyperparameter choice. But people usually use quite low dimensional arrays, since otherwise like just becomes too big.
No. When you're looking at a harmonic, so you're looking at a function on a symmetric power. What power do you do? Can you do more?
We look at the full Peter-Weyl decomposition, but then for a specific choice of input and output representation, these Clebsch-Gordon coefficients, almost all of them become 0. So let's say if you want to map, if you have SO3 and you want to map from order J to order L, then actually the allowed frequencies go from J minus L up to J plus L. So you have like a natural highest cutoff, and if that's too high for whatever reason, you can also manually take out certain degrees of freedom. All right, so yeah, the issue here is that what we are assuming in these theorems here is that we have a compact group. Now the question is, how do you generalize that to non-compact groups? And there's an alternative way to implement that, which is by implementing the convolution kernel itself as a neural network, which is possible since convolution kernels, as I said, are just maps from Euclidean space into matrices. So you can just parameterize this thing as a multi-layer perceptron and then learn the kernel like that. So this is what you see here. You input coordinates into a neural network, and then you get a matrix valued field out. And in the case of steerable kernels, what you have in addition is this G-steerability constraint, which is just an equivariance constraint. So you act on your input coordinates. This K of Gx equals, here you act with this tensor product representation of rho in and rho out. And you just need to ensure that this MLP here is equivariant with respect to these representations. And yeah, the point is essentially that we don't know how to solve the kernel constraint for non-compact groups, but we know for certain non-compact groups how to implement multi-layer perceptrons. So in particular, we have this one paper where we have we're using these Clifford steerable convolutions. So basically, we use the Clifford algebra to implement Lorentz group equivariant MLPs, which we can then use for convolution kernels. And the Lorentz group is not a compact group, but with this approach, we can actually still kind of solve such kernels.
What's the nonlinearity in the MLP?
In the MLP. So in these Clifford MLPs, you're using tensor products of features with themselves. That is one thing people do, and another thing well, it's essentially the same thing, but gated nonlinearities.
So that's the nonlinearity is coming from the tensor product features.
Yeah. That's one choice, but another one is a gated nonlinearity, where you take scalar features, you apply some sigmoid or some gate on it, and then you multiply these to your other non-scalar features. So there are certain hacks people are doing.
Can you say again what the issue is with the kernel constraint in the non-compact case? You said you weren't sort of able to do it.
We just don't know how to solve it analytically. And we have this solution here, but these decompositions here, they are theorems. Like this Peter-Weyl decomposition, they assume compact groups. And I could imagine that physicists actually solve that specifically for the Lorentz group as well. But yeah, our formulation of the theorem doesn't cover it.
But I think you are going in the right direction, no? Because like there are no finite dimensional unitary representations of non-compact. So you are using an MLP to characterize it, right?
Yeah.
I mean, I was guessing something of that sort.
Yeah, I have no idea how to solve it, but yeah, that could be an approach. All right, and then yeah, that used to be an animation, but it was squashed and that's a PDF, so it's not animated. But one advantage of that approach is actually that we don't only so usually we would only input coordinates here, but actually you can throw in all kinds of additional conditioning features. So if you do message parsing, you can throw in not only this relative edge vector here, but also features from nodes I and j. So for instance, if that node here would be associated with mass or something like that, that could also be input to that network. And then the convolution kernel actually depends now also on features. And this is exactly what you have in a transformer. Since in a transformer, you're kind of linearly aggregating tokens from other positions in such a way that this aggregation itself depends on inner product between queries and keys, which are essentially features. And here our aggregation also becomes dependent on input features, which makes this quite more powerful, and the performance of these networks is higher than if you would just have a steerable basis. All right, so if you want to use these networks, we actually have a library, a PyTorch library, which implements such steerable CNNs for any subgroups of OD in 1, 2, or 3 dimensions, and arbitrary field types, so you can pick whatever representation you like. And I have 2 code snippets here showing you how you would use it. So if you want to implement a convolution in native PyTorch, you just have this nn.conv3d, you pick a certain number of input and output channels and a certain kernel size, and that is your convolution operation. For us, it looks a little bit more complicated. First, we need to fix the symmetry group and the group action on our space. So yeah, in this case here, what I chose is we have a 3-dimensional space, but then we use a cylindrical action. So just imagine you are in R3, and then you have gravity breaking the symmetry such that you are left over with rotations around the z-axis. And then this n equals 16 means that in addition you are discretizing that SO2 rotation symmetry to 16 discrete steps. And then you need to choose your input and output field types, which are just these representations row in and row out. So for instance, you can choose 4 trivial representations for scalar fields, then you could choose 8 times irrep of type 1,1, 16 regular representations, and so on, really whatever you like. And then maybe you want to map to 3 output regular representations. And then instead of passing, so we have our nn.r3conf, instead of nn.conf, and then instead of passing input channels and output channels, we pass in input field types and output field types, which imply a certain number of channels, but on top they imply this steerability constraint. And the library internally solves everything and gives you a complete basis of these kernels. And then you're guaranteed that the symmetry is solved and that you are mapping correctly between field types. So some empirical results, for instance, for image classification, we did that a few years ago for Cypher 10, Cypher 100, or SCL 10, which are bigger images. And then we just take a CNN baseline, and we see that if we just take these models and plug in our steerable kernels, the test errors become much lower. So we go from 2.6 to 2.05, or from 17.1 to 14.3, or from 12.74 to 19.8, which is quite considerable given that we didn't tune anything. We just plug in our convolution kernels and that's it. And these are actually natural images, so you wouldn't even expect that rotation equivariance would be helpful, but apparently it is. And what you see here on the left is the loss curve, the training loss curve for conventional CNN here in blue. And then if you have the cyclic groups of order 2, you have rotation equivariance with respect to 180 degrees rotations. Then here for C4, 90 degrees, 45 degrees, and so on. And you see that the models converge faster and faster and do better final performance if you make them equivariant. Yeah, and then this is actually not our work, but from a different group. And they used our models to train robots to kind of like that robot arms, which should learn to pick some objects and place them, for instance, in a bowl or something like that. And yeah, the non-equivariant model didn't even converge, while our equivariant models converged quite well. And then as a last example, for these Lorentz equivariant convolutions, we had some simulations where we have electromagnetic field dynamics, and we show the neural network the past, I don't know, maybe 16 time steps or so, and want to predict the next 16 time steps. Then we measure the mean squared error. And what you see here is the blue curves are the performance of a non-equivariant network, where going from here to here, we increase the dataset size, and then at some point, the network just saturates and doesn't become any better, while our model is, even with very small dataset sizes, is already much better. All right, so now we'll come to manifolds and gauge symmetries, but I'm seeing the time is almost over, so I will probably quickly go over that. Yeah, so until now we talked just about Euclidean spaces, but you can generalize that in two different directions. The first one is homogeneous spaces. So that would be, for instance, something like a sphere or so. So any space where you have a transitive group action. And then we can also go to general Riemannian manifolds. So let's first look at homogeneous spaces. The idea which we used up to now carries over one-to-one. It's basically the same strategy, which means we demand equivariance, and from that we derive convolutions or weight sharing. So yeah, in the first example, we had basically Euclidean space as a homogeneous space under translations, and then you get weight sharing over your whole space. And that works for any other homogeneous space as well. So for instance, if you have a cylinder, and then your group action could be something like rotating around the cylinder and moving up and down. And that, again, if you demand equivariance with respect to that action, again, you get weight sharing over the cylinder. And then we had this bit more complex example where now here we are again back to Euclidean space, but we have the affine group as transitive symmetry group. And then we got this G steerability constraint, and G is essentially the stabilizer subgroup of that action on this space. And this is how it generalizes to general homogeneous spaces. So let's say we have, for instance, S2, the two-sphere, and we want to have a neural network which is SO3 rotation equivariant. So if we take our feature field on the sphere and rotate it around, then we want to commute with that. And again, in that case, SO3 has a stabilizer subgroup SO2 on the sphere. So just imagine you take the North Pole, then you have rotations around the North Pole in SO2, which fix the North Pole. And that again implies that you need SO2 rotation steerable kernels to implement that. And yeah, so what you're seeing there in top right is the paper is called Intertwiners between induced representations. And the thing here is that this global symmetry group here, we have this global symmetry group, then we have the stabilizer subgroup, and we have these spaces here, and they relate such that. So yeah, we have the global symmetry group, which I just call H. Then we have a stabilizer subgroup, which we used to call G. And basically, we have that space, which corresponds to the quotient map of H is a subgroup of G. Sorry, G is a subgroup of H, this way around. And you get a quotient map here, which goes to the quotient of H with respect to G. And that is the space we are operating on. So in that example of SO3, you would have basically SO3 and the quotient map to SO3 quotient SO2, which is isomorphic to S2. And this here is essentially a principal bundle. And the feature spaces we are operating on are associated vector bundles to these principal bundles. And sections of these associated vector bundles basically implement what is called an induced representation. So there's really a fiber bundle interpretation of behind all of that. So this is the theory for homogeneous spaces. And then I just quickly mentioned before I stop, for Riemannian manifolds, we would in principle like to apply the same idea that we start with equivariance and derive weight sharing for it. But the issue here is that Riemannian manifolds are in general asymmetric. So let's say we have this egg here, then you have rotations around that egg. which means you get weight sharing on these symmetry group orbits, but they are not transitive any longer, so you won't get weight sharing between different orbits. And if your manifold is completely asymmetric, you don't get any weight sharing, so that doesn't bring you any further. But yeah, I will just end with this intuitive notion of how we solve that. So you can think differently about convolutions as basically taking a kernel and applying it at every point of space. So we can try to do that now on Riemannian manifolds. But the issue is that if you have a convolution kernel and you want to place it somewhere, you don't know how to, for instance, rotate the kernel. Right? So you have this ambiguity of kernel rotation. And intuitively, that's again solved by using G-steerable kernels. Since let's say you have a rotation steerable kernel, then you don't care how you place it. Since if you choose a different kernel orientation, you essentially get the same output, but acted on by the representation, which means it encodes exactly the same information relative to a different choice of reference frame. Yeah, and that is basically the intuition that like these different choices of kernels can be identified with different choices of reference frames or sections of your frame bundle, essentially. And then I called it initially coordinate independent convolution network. So all we are demanding is that our neural network is independent of these choices of frames. And then if you do the home ops behind it, again, you get that your kernels need to be steerable. So you can derive the steerability from coordinate independence. But now it's a coordinate independency in the sense of that you have at each tangent space, at each point in space, you have a choice of reference frame which you can transform independently. And that is this local notion of gauge symmetry we are looking at. All right, so if you want to learn more about that, we are actually soon publishing a book on this topic, which is together with Patrick Forer, Eric Verlinde, and Max Weiler.
Situation where you applied just manifold networks.
Yeah, so initially we implemented that on icosahedron, which you can think of as a approximation of a spherical CNN, but you have like these locally flat faces, which makes it very performant. And that was more or less like just a showcase of how to implement that. People implemented it for spherical CNNs, but we also have an implementation on just meshes, like flat meshes in computer graphics. And people applied that for, I showed that visualization at the beginning of that chapter. Basically, they had meshes of, this is an artery, which is modeled, and they want to predict something about like the flow of blood through that artery, and or the wall shear stress on that artery or something like that. And you can predict that with these neural networks.
We're going to do some metric on subspace.
Mm-hmm.
You have some differential equation, or you have some data, some experimental data from astrophysics, cosmology. Would you be able to, you would have different morphism invariance?
Yeah. Yeah, that's possible. So in principle, if you want to predict the metric, that's just a tensor field, right? So you can do these convolutions, and like your final layer would output a tensor field, symmetric tensor field of the correct representation type. That's possible, and then yeah, your G would probably be the general linear group, just basically what you have in general relativity. The only issue is that you would have to implement it in four-dimensional space-time, I guess, for the practical applications, and then everything becomes too high-dimensional to implement it. Since you have like this four-dimensional space-time, and then you have like your channels, which kind of explode with very high-dimensional representations, and then you also have the depth of the network. So I think memory-wise, it's not possible yet, but in principle, you could do it.
Yeah, but that's what I was saying. This different approach where you actually are using the point cloud structure and you have normal MLPs like taking the four vectors directly, and you can actually input invariance, equivariance. That seems to be a bit more efficient for higher dimensional space.
You mean this
You know,
group
the
averaging?
Pythagoras, these things, or the scalars are universal paper, where they use this invariant theory resource.
Oh yes, okay. But in that case, they are only talking about sets of representation vectors. Yeah, I know what you're talking about. It's basically a set of vectors where we have a field of vectors. So that's a very different application.
No, yeah, but what I'm saying is like, if you are interested only in learning a proper function, maybe not for the tensor field, but if you are only interested in learning an invariant function finally, then that seems to be much more.
Yeah, but they're assuming, so we are operating on so-called induced representations, and this paper is talking about non-induced representations, just irreps of the orthogonal group, but not of the Euclidean group. So you can't even apply it to that case.
You can. I mean, orthogonal group, but that's actually the inhomogeneous orthogonal group, which is the Euclidean group.
Okay, so maybe in that case, that's okay.
Maybe one short question in the CFAR experiment, you shown the CNN get the data augmentation.
Oh yes, all models are trained with data augmentation. Yeah.
And there seems to be a lot of choice in what kind of representation you want to generate in the inner layers, presumably the bad and good choices.
Yeah.
Do you have any situations? Is that just a search space?
Yeah, essentially it's a search space.
But CNN in some cases, for instance, if you choose something too complex.
Yeah, what works well is if you choose regular representations of your group. And this is why in this example here I use this n equals 16, since regular representations are essentially functions on the group, which if you have a continuous group, it becomes an infinite dimensional representation. But if you go to this cyclic group of order 16, then you get at each point like a 16-dimensional feature vectors where these 16 entries start permuting around. That becomes too high dimensional for big groups, but at least this is still feasible and then usually works best.
Question on one of the slides you skipped.
Okay.
Yeah, so it's.
Which one?
I think I saw the word lattice somewhere.
Oh yeah, that's the very last one. Yeah, I included that since we were like I want to talk about like the gauge theoretic viewpoint here and make a connection to lattice gauge field theory. And basically what you have in our case is that at each node of the lattice you would have a feature vector, right? While in lattice gauge theory you would have something like a fermion at each lattice vector. The difference is already that our features are associated to the tangent bundle. So there's some spatial symmetry group action on them, while for fermions you have like these internal quantum space representations acting on them. That's one difference. And then the other difference is edges correspond in our case to the connection or parallel transporters, something like the Levi-Civita connection or whatever you're using. While for lattice gauge theory, you have gauge bosons on your edges. And we are usually assuming that in geometry, so the connection is fixed. So we are just interested, we just have these nodes here, feature vectors have nodes as features, while papers which are trying to solve something like lattice gauge theory, quantum problem dynamics or so, they are usually interested in sampling these edges, the connection itself. And that becomes quite complex since now your features are group valued and it's not entirely clear how to implement that. So there's some connection you can draw, but it's like fundamentally a different problem in the sense that they're interested in solving for the connection while we just take it as granted.